Okay, let's unpack this. Today, we are diving into one of the most consequential and, frankly, one of the most infuriating stories in modern technology.
That's a big one.
It really is. This is the definitive origin story of generative AI, tracing the moment a single breakthrough paper just transformed computing forever. And this isn't just a technical history, right? It's the ultimate corporate cautionary tale.
It absolutely is, and the drama here is just immense. Our source material today centers on 8 Google researchers who, back in the spring of 2017, published a paper called Attention is All You Need.
That title is now iconic
Yeah.
because that paper introduced the transformer architecture. That is the engine, the foundational T in every single large language model you hear about today.
Every single one. GPT, BERT, Claude, Llama.
All of them. Every competitor, every billion-dollar valuation, it all stands on the shoulders of that single breakthrough.
So our mission in this deep dive is, kind of twofold. First, we have to explore the sheer technical genius that it took to birth this technology because it fundamentally solved AI's big scalability problem. But second, we have to dissect the surprising corporate oversight they encountered at Google. And that led to this incredible multi-billion-dollar exodus, what people are now calling the transformative diaspora.
We are talking about how the single most valuable piece of intellectual property in tech today, the very heart of the global AI arms race, didn't just get stolen. It effectively walked right out the door.
Yep. Packed its bags and left.
It left Google's payroll and immediately started fueling their primary multi-trillion-dollar competitors. We'll look at exactly what the paper solved, the surprising roles the 8 inventors played, and then the multi-billion-dollar ventures they built after they left.
And what's so fascinating here is that the creation of this architecture was really just the opening act. The flight of talent that came after, it just dramatically accelerated the global AI arms race.
It forced everyone's hand.
Everyone's. It forced every major tech company, including Google itself, to compete directly against its own former architects. It's a strategic boomerang that is still playing out today. We will analyze precisely why the culture of caution and institutional inertia allowed this unparalleled transfer of core expertise to happen.
The tacit knowledge.
That's the key. Researchers call it the non-codified critical tacit knowledge, the stuff you can't write down in a paper.
And to give you a genuine sense of the scale here, and this is the shocking statistic for you, the learner, the sources show that the companies founded by these 8 individuals have collectively raised venture capital exceeding $2 billion.
$2 billion. That's immediate, massive financial validation.
It proves the immense commercial value of that initial breakthrough that Google seemingly, just completely undervalued and then lost control of. We're going to break down how that loss really defined the current era of technology.
Right.
Okay, so to truly appreciate the revolution, we have to start with the technical ceiling AI was hitting right before 2017.
Right, the state of play.
Exactly. If you were working in sequence modeling, so tasks like language translation, speech recognition, anything involving ordered data, you were using recurrent neural networks, or RNNs.
Or their fancier cousins, LSTMs and GRUs.
Right. But these systems were just running into brick walls. What were the core, the intrinsic limitations that were holding them back?
The primary constraints were just fundamental to how RNNs operated. It all stemmed from their need for sequential processing.
Meaning one thing at a time.
One thing at a time. Imagine trying to read a very long sentence, but you can only read it one word at a time, and you're only allowed to remember, say, the last 5 words you read perfectly. That was kind of the RNN dilemma.
So the architecture was trying to mirror human reading, which sounds intuitive, but in a computing context, that means every step depends entirely on the completion of the step before it.
Exactly. And that dependence meant that true parallel processing was either impossible or just extremely inefficient. You couldn't run sections of the data at the same time across multiple computing cores or GPUs.
So the training times must have been astronomical.
It's dramatically longer. As data sets grew from gigabytes to terabytes, the training time just scaled impossibly high. They simply couldn't scale efficiently enough to handle the sheer volume of language data you need for general intelligence.
Okay, so that's problem number 1, speed. What was the second, equally damaging problem? The sources talk about the long-term dependency problem.
Right, and this often showed up through something called the vanishing gradient problem.
Can you elaborate on that? Because LSTMs, the long short-term memory networks, they were specifically designed to help with memory, right? But they still failed over long sequences.
He did. LSTMs and GRUs, they introduced these gates that helped maintain a state, a kind of memory, over longer stretches than a simple RNN, but they couldn't fully solve the problem.
Why not?
The core issue of the vanishing gradient is that as the error signal, the gradient propagates backward through all these layers and time steps during training, it just shrinks exponentially.
It gets weaker and weaker.
Exactly. By the time it reaches the early parts of a long sequence, the signal is so weak it has vanished that those early elements, they just can't update their weights effectively. They don't learn.
So if I'm trying to translate a complex German sentence where the verb is famously at the very end, the model might have literally forgotten the subject of the sentence by the time it gets there.
Precisely. That forgetting meant that the network became less and less effective at learning the precise contextual information about words that appeared far apart in a sentence.
Which is, I mean, all of human language.
Right. So this set an artificial hard ceiling on scalability and performance for any task requiring long sequences.
Slow processing and a limited memory span. I mean,
Yeah.
that sounds like a technical limitation that just guarantees mediocrity.
It was, and that is precisely what the transformer architecture was designed to blow apart. The breakthrough idea from the Google team was to propose the first transduction model. So, a model that transforms an input sequence into an output sequence, like translation, that relied entirely on the attention mechanism.
And this allowed them to just discard the sequential steps imposed by recurrence and convolution.
Completely, they threw them out.
Okay, let's zero in on that core innovation then. The self-attention mechanism. How does it fundamentally solve both the speed and the memory problems at the same time?
Self-attention allows the model to capture contextual information from the entire input sequence simultaneously.
A whole thing at once.
A whole thing at once. So think of it like this. Instead of reading a sentence word by word, the transformer reads the whole sentence instantly and asks, for every single word, how important is every other word in this sentence for understanding this specific word?
Okay, can you give us an analogy for how that instantaneous context search happens? I know it uses these query, key, and value vectors, or QKV.
Certainly. So imagine you are using a really sophisticated search engine to understand a complex document.
Okay.
First, you have the query queue. This is the current word you are trying to understand. It's your search term. Second is the key, K. This represents the metadata or the index of every other word in the sequence. And third is the value, V, which is the actual contextual information of those other words.
So Q is what I'm looking for, K is where I look, and V is what I find.
A perfect way to put it. The attention mechanism calculates an attention score by comparing the query of your current word against the key of every single other word in the sentence. If the query matches a key, the score is high, meaning that word is contextually relevant. These scores then determine how much weight or focus the current word should place on all the others.
So the key phrase in the paper was basically, pay attention to specific words no matter how distant they are.
Exactly. Distance becomes irrelevant. And the parallel processing comes into play because the model calculates these QKV interactions for all words concurrently, right? Not one after the other.
Right, that's the engine of the speed increase. Since every token's attention scores can be calculated simultaneously, the entire input can be processed in one massive parallel operation.
And that solved the training time bottleneck instantly. It moved AI from the domain of weeks of sequential training to, days or even hours of parallelized training.
Just a total game changer. And then there's the second layer of genius, the multi-head attention, MHA mechanism. Why wasn't one attention function enough?
MHA provides specialization. A single attention function might only look at one type of relationship, maybe simple word proximity or something. But MHA runs multiple heads, often 8 or 16 of them in parallel. And each head learns a different specialized aspect of the relationships within the sequence all at the same time.
You called them specialized interpreters earlier. Can we expand on that? Like, what different perspectives are these heads actually capturing?
Yeah, think about the complexity of human language. One head might become an expert in, say, syntactical dependencies, recognizing grammatical roles, like which noun is the subject and which is the object.
Okay, the grammar cop.
Exactly. Another head might specialize in semantic relevance, identifying words that are related by theme or meaning, even if their grammar roles are totally different. And a third head might capture something like anaphora resolution, figuring out what the word "it" refers to 5 sentences earlier.
That's fascinating. So by running all these specialized interpreters simultaneously, the model builds a far richer and more, nuanced contextual representation of the input.
Absolutely. The outputs from all these specialized heads are then concatenated and fused together into a single comprehensive vector representation. This concurrent multi-perspective processing, it just dramatically increased the model's overall robustness, its accuracy, and its generalizability.
And what was the measurable, undeniable proof that this architectural shift was a revolution? Not just an improvement, but a true revolution.
The proof was immediate and it was undeniable. The architecture demonstrated a massive step function improvement in performance benchmarks. In machine translation, the transformer architecture achieved over 2 BLEU point superiority against the existing state-of-the-art models.
For our listeners who might not be familiar, what does a BLEU point represent in this context? Is 2 points a lot?
2 points is huge. The BLEU score, or Bilingual Evaluation Understudy score, is a standard metric for measuring the quality of machine-translated text compared to high-quality human translations. Historically, gaining even a fraction of a point was considered a major research success.
So getting 2 full points was just off the charts.
It indicated a paradigm shift. And crucially, the transformer achieved this higher performance while training in a fraction of the time. This combination of superior quality and massive speed, that's what unlocked the scaling era that defines modern AI. Hashtag Tech2. The team transformer and the quiet revolution.
So that's the technical context. Now let's look at the people who executed this. This breakthrough wasn't the product of a single genius in a garage. It emerged from this intense collaboration within Google Brain and Google Research in the spring of 2017.
Right. 8 names were listed as authors on Attention is All You Need.
And this story really highlights the serendipity of research, doesn't it? The 8 authors, they represented this convergence of talent linguists, computer scientists, machine learning experts. Some had worked closely, others were almost strangers.
Yeah, take Jacob Busqueit. He's often described as the intellectual instigator. He was the one who proposed the radical, almost irreverent idea. Let's just scrap recurrence altogether and just use attention.
That's a huge technical gamble to take. So what happened after that initial spark?
It required immense follow-through, and that's where Ashish Vaswani and Ilya Polasukin were key. They were the ones who designed and implemented those initial models, converting Busqueit's radical concept into a working computational reality, proving the hypothesis that attention alone could actually deliver results.
And then there's Noam Chazir. The sources describe him with this almost mythic reverence, a wizard, a genius. He took the early promising but maybe clunky concept and engineered the essential components that made it industrially viable.
Chazir's role was truly paramount. While the initial attention idea was radical, it was Chazir who introduced the practical necessities. Things like the scaled dot product attention, which stabilizes the calculation,
Okay.
and the crucial multi-head attention, which we just talked about, that provided the diversity of perspective and also the clever parameter-free position representation.
Wait, position representation. If the model is processing everything in parallel, how does it know the order of the words anymore? It loses the sequential information that RNNs inherently had, right?
That's a critical point and a huge problem they had to solve. Chazir solved this by introducing positional encodings. Instead of learning the order, which takes computational power, they simply inject information about the relative position of each token into its input vector.
So it's like a little tag on each word.
Essentially, it tells the model, hey, I am the 3rd word, and this other word over there is the 10th word. It's an elegant, computationally cheap solution that preserved the parallel speed while regaining the vital sequential context.
And there's a great human moment attached to Chazir's contribution. When he saw an early draft of the paper, he was apparently surprised that his name appeared first in the authorship list.
It really speaks volumes about the collaborative spirit and the focus on the science, not on the credit. Chazir himself admitted he wasn't thinking about it. But the team clearly understood that his engineering contributions, those crucial practical components, were what elevated the transformer from an interesting experiment to a robust paradigm-shifting architecture. His work basically ensured the model functioned robustly and efficiently at scale.
So the team quickly realized this was far bigger than just fixing machine translation benchmarks.
Yeah.
What was their broader vision at that point?
Their vision expanded very rapidly. They started experimenting with diverse tasks, like generating Wikipedia articles and various parsing challenges. And this experimentation quickly convinced them that the transformer was not just some niche tool.
It was a platform.
It was a powerful general-purpose language model. They knew, as one source put it, this is more than better translate. This is a new platform. They saw it as the engine for general intelligence.
Yet, despite the inventors knowing they had engineered this tectonic shift, Google's perspective at the time was famously cautious, or as you termed it, cooler on the paper. Why the disconnect?
I mean, Google at the time was still heavily structured around its core business, search and advertising. It was powered by a very incremental approach to AI improvement. They viewed the paper as simply the next iteration of our language model work coming out of Google Brain.
Just another paper.
Just another in a long line of state-of-the-art papers. They saw it as research output, not a brand new commercial franchise.
We have to be clear, though, as you noted, it's a false narrative that Google ignored the technology. They were actually very quick to adopt it internally.
Oh, they were lightning fast internally. Within a year of the paper's release, Google launched BERT, which stands for Bidirectional Encoder Representations from Transformers.
And BERT was one of the first genuine large language models.
It was, and they integrated it directly into search results.
So what exactly did BERT do to improve Google search? How did a regular user experience that?
BERT fundamentally changed query comprehension. Before BERT, search relied heavily on just keyword matching. So if you search for a complex, nuanced question, the search engine often struggled to understand the relationships between the words.
It would just pick out the nouns and verbs.
Exactly. BERT, using its transformer architecture, could read the entire query bidirectionally. So it analyzed the context both forward and backward to grasp the intent and the meaning of the search string. This resulted in a massive immediate jump in search quality for complex or conversational queries. So Google absolutely leveraged the technology in its most important product.
Okay, so if they used it internally and saw the massive improvement, where was the fatal flaw? If they had this incredibly powerful model in their most valuable product, why did they lose the architects?
The fatal flaw was one of imagination and strategic commitment. Google failed to recognize a transformer as a wholesale technology platform change that demanded massive, immediate commercial deployment outside of their existing products.
So they saw it as a feature, not a new company.
Precisely. They allowed the paper to be openly published, which was consistent with their open source research culture, but then they failed to create the commercial, entrepreneurial environment that would keep the architects interested in scaling it into a general-purpose, product-first franchise. They published the blueprint, but didn't commit the resources to build the skyscraper.
And they had the resources. They had the TPUs.
They had the perfect infrastructure. Their proprietary TPUs, tensor processing units, were ideally suited for the massive matrix multiplications the transformer required. They had the ability to dominate the nascent LLM space from the very beginning. But their cautious, research-oriented approach just ceded the critical first-mover advantage and, worse, the talent.
And the legacy is just undeniable. The paper has been cited over 173,000 times as of today, making it one of the most cited scientific papers of the 21st century. It's a foundational text for an entire industry that was conceptually invented and then strategically abandoned by the very company that developed it.
This brings us to the strategic vacuum that developed almost immediately after publication. The sources indicate that management's attention, including then CEO Sundar Pichai, was split. There was reportedly this prevailing desire to see what others did with it first before fully committing the vast organizational resources required to pivot the entire company around this new architecture.
That wait-and-see posture, trying to mitigate risk, ended up creating the biggest risk of all, the immediate loss of the human capital. All 8 original co-authors ultimately departed Google. What was the driving motivation for these world-leading researchers to leave the best-resourced AI lab on the planet?
The motivation was consistent and it was clear. It was frustration with institutional inertia.
The bureaucracy.
The bureaucracy. They were foundational researchers who recognized they had invented the engine for general intelligence. They sought the operational freedom necessary to execute that grand vision, to scale the transformer into a massive, standalone, consumer-facing or enterprise-facing product.
And they felt blocked.
They felt this vision was continually blocked by corporate bureaucracy, cautious prioritization, and a culture that was focused on incremental improvements to the search business rather than radical platform-level risk. I mean, to put it simply, they wanted to build general intelligence. Google wanted to improve ad targeting.
This is where we return to that crucial distinction between explicit knowledge and tacit knowledge. Google published the explicit knowledge, the blueprint, by releasing the paper openly. But the architects took something far more valuable with them when they left.
They took the tacit knowledge. This is the non-codified expertise that you cannot write down in a paper or patent. It is the practical wisdom that's required to execute at scale.
Okay, let's dedicate some time to defining this. What specific elements of tacit knowledge did Google lose that were so valuable to the competition?
Well, tacit knowledge in this context includes things like, first, scaling methodology. So knowing precisely how to distribute a model across thousands of TPUs or GPUs efficiently, the exact communication protocols, the batch sizes, the data parallelism techniques that prevent the whole system from crashing at 100 billion
The
parameters,
stuff that only comes from trial and error.
hundreds of failed experiments. Second is hyperparameter tuning wisdom. The specific, often counterintuitive settings for things like learning rates, optimizers, and dropout rates that allow these large models to train stably for weeks without exploding gradients.
The secret sauce.
It really is. Third is data hygiene and curation. So understanding which specific data sources, which filtering techniques, and which tokenization methods yield the highest quality outputs. Knowing what makes the model smart isn't just about the data volume, but the data purity.
And finally, just the operational stuff.
The operational know-how. The ability to troubleshoot catastrophic memory failures or hardware communication issues that are totally unique to these massive distributed systems.
So that deep, hard-won expertise, the what works, that wasn't included in the appendix of the paper, that's what rivals paid billions for. The talent was the control point.
Exactly. When the inventors left, they didn't just transfer an idea, they transferred a fully operational, high-performance R&D capability, and that instantly accelerated the global AI arms race for their rivals.
Okay, let's quantify this competitive fallout, the transformative diaspora, by looking at the ventures that sprang up and the immediate capital validation they received.
We can trace their influence across every high-value segment of the AI economy. Let's start with Aidan Gomez, who founded Cohere. He explicitly decided not to go after the consumer chatbot market initially.
A different strategy.
Very different strategy. He positioned Cohere as an enterprise AI leader. Their focus is B2B, centered on security and data control.
What does that B2B focus actually entail in practice?
It means they focus on secure, sovereign AI solutions. These are often designed to run AI workloads on a company's own premises or in their private clouds to meet strict data compliance and governance needs. This is crucial in fields like finance, healthcare, and government.
And it paid off.
Hugely. This strategy earned Cohere a valuation between $6.8 and $7 billion, demonstrating the market's huge appetite for enterprise-grade, controllable LLMs.
Then we have Noam Shazir, who co-founded Character.AI. His venture took the complete opposite approach, focusing purely on consumer conversational AI and engaging chatbots and personas.
Right. And Character.AI, through its viral consumer success, achieved a $1 billion valuation after raising $150 million. It capitalized on the social and entertaining aspects of LLMs, proving that the technology was ripe for consumer adoption. It's a stark contrast to Cohere, and it just shows the transformer's versatility.
And of course, Shazir's story is complex, as he later rejoined Google DeepMind in 2024 to lead the Gemini effort, a critical, high-value reacquisition.
The prodigal son returns.
Exactly. Let's move to Ashish Vaswani and Nikki Parmar, who founded Essential AI in 2023. What niche are they targeting?
Essential AI is focused on efficiency and enterprise automation. Their goal is to develop full-stack AI products that automate core workflows for companies, aiming to make human analysts, 10 times faster. Their stated goal is optimizing user value per computational resource used.
That's a fascinating metric. What does optimizing user value per computational resource really mean in practice?
It means they recognize that the cost of running massive AI models is just unsustainable for every single enterprise task. So they prioritize developing smaller, fine-tuned, and highly efficient models that can deliver precise, high-value outcomes like summarizing long legal documents or analyzing proprietary company data without requiring the vast, costly computational resources of a GPT-4.
So they're selling precision and cost efficiency.
Exactly. And they secured $56.5 million in Series A funding, with Google itself later becoming a strategic investor, which is just incredibly ironic.
The diaspora also moved into the world of Web3 and decentralized systems with Ilya Polasukin.
Polasukin left Google early, back in 2017, focusing on the future of AI governance and decentralization with Near protocol. His work centers on using blockchain for global micropayments and distributed work coordination, pioneering something called decentralized confidential machine learning, or DCML.
What's the vision there?
He anticipates a future where AI training and inference happens across a distributed network of compute power, rather than solely within massive centralized data centers owned by a few corporations.
And we have to mention Jacob Uskarate, the instigator of the original idea, who co-founded Inceptive. His work is a powerful testament to the transformer's generality.
It really is. Inceptive applies the core transformer architecture to biology, specifically to designing RNA molecules for applications like new therapeutics and medicine. It treats the sequence of nucleic acids in RNA as a sequence just like human language.
The same fundamental
Yeah.
problem.
Exactly. It demonstrates that the attention mechanism is a general-purpose model for understanding any sequence data. They've raised $20 million, showing that this language capability extends far beyond words.
And finally, there's Lion Jones, who not only co-authored the paper but actually coined the term transformer. He founded Sakana.AI, which is focused on integrating concepts from nature and biological systems into AI, a fascinating new direction he calls nature-inspired intelligence.
So when you total the capital, the collective funding secured by these startups has surpassed $2 billion. This isn't just about financial success. It proves that investors immediately grasp the strategic value of the tacit knowledge that Google failed to retain.
The diaspora didn't just scatter into obscurity.
Not at all. It crystallized into numerous, highly capitalized ventures aimed directly at reinventing entire industries based on the technology they invented at Google. #TerryRV, the strategic aftermath, and AI's trajectory. And the corporate exodus wasn't a contained internal problem, right? It fundamentally destabilized the competitive balance. The loss of talent directly and dramatically aided Google's biggest existential rival, OpenAI.
And the most significant talent transfer was Uka's Kaiser.
Yes, he left Google in 2021 to join OpenAI as a senior research scientist. And this wasn't just a loss of a researcher, this was the transfer of deep primary architectural expertise right into the competitor's central R&D team as they were developing their most potent models.
So he brought that tacit knowledge with him.
Absolutely. Kaiser is credited as one of the co-inventors of the highly secretive foundational model often referenced as Q. He also contributed significantly to the development of GPT-4 and the subsequent GPT-5. His move provided OpenAI with the foundational scaling and implementation expertise that dramatically accelerated their transformer development curve.
Let's pause on Q. For our listeners, what is the rumored significance of Q, and why does Kaiser's involvement confirm this strategic loss for Google?
So Q is rumored to stand for Q-learning combined with A-search. And it is believed to be OpenAI's effort to move past pure token prediction toward genuine reasoning and generalized problem-solving capabilities.
A step towards AGI.
Potentially. If Q is focused on planning and advanced reasoning, Kaiser's expertise in architecting stable, massive, complex models is absolutely crucial. The fact that Google's former architect is spearheading the development of the rival's potential general artificial intelligence breakthrough, it just confirms that Google lost not just employees, but the trajectory of global AI development.
And Google's initial strategic failure then necessitated this costly, almost embarrassing re-engagement, what you termed the boomerang effect.
The boomerang effect is the ultimate evidence of the strategic mistake. We see it in two key actions. First, Google becoming a strategic investor in essential AI, effectively paying its former employees to deploy industrial AI solutions using the architecture they invented.
And second, even more dramatically, the high-value reacquisition of Noam Shazir in 2024.
Yes, Shazir, the man who provided the practical components that made it all work, returned to lead Google's primary LLM effort as the Gemini technical co-lead at Google DeepMind.
That decision to pay a premium to lure back the talent they let walk away is the clearest confirmation that the expertise was strategically indispensable and, initially valued far too low.
They realized they could replicate the code, but they couldn't replicate the collective wisdom and leadership required to scale Gemini to compete with GPT-4.
Now, here's the irony. Even as the transformer architecture completely dominates global AI research, some of its original architects are expressing significant frustration with the status quo.
Yes, the inventor is tired of his invention. Lion Jones, the man who coined the term transformer, gave an unusually candid assessment stating that he is absolutely sick of them.
Sick of them. That's a provocative statement. What is the core concern underlying that frustration?
His core argument is that the entire field has calcified around a single architectural approach. He believes that despite the massive investment, the billions of dollars, the huge pools of talent, the pressure from investors demanding returns has caused a dangerous narrowing of research.
So everyone's just iterating.
Everyone is simply iterating on the transformer model, making it bigger and slightly more optimized, rather than searching for the next truly foundational breakthrough.
This sounds like the commercialization trap.
It is. The trap is that corporate and investor pressure prioritizes profit extraction and scaling existing proven models over the radical, high-risk, non-transformer research required for the next paradigm shift. Since the transformer is a known quantity with a clear path to monetization, just make it bigger, companies are incentivized to forego the kind of quiet, deep research that led to the original 2017 paper.
And this period also cemented the reality of what researchers call the bitter lesson.
The bitter lesson is the harsh realization in AI development that once a scalable architecture is found, and the transformer is the ultimate scalable architecture, the key to improved results is simply scaling.
More data, more compute.
That's it. Intelligence, at the massive scale unlocked by the transformer, becomes less about algorithmic cleverness and more about sheer computational muscle.
And the proof is in the parameters.
Absolutely. The first models, like GPT-1 and BERT, showed state-of-the-art performance. But then subsequent models just pushed the limits. GPT-3, with 175 billion parameters, and GPT-4, estimated at 1.7 trillion weights. The trajectory shows that massive size and massive compute are the primary drivers of performance, validating the scaling mantra that the transformer enabled. The architecture fundamentally changed the economics of intelligence, finding a path where exponentially more energy and data always yields incrementally better results. #TagV, broader implications, and future focus. And the sources highlight that the strategic challenge of retaining foundational AI talent, it's not just a Google problem. It's a global economic and national security issue. Nations are struggling to secure their local AI talent against the draw of massive U.S. venture capital funding.
Taking the UK example cited in the sources, what are the key policy recommendations for national governments and research institutions to prevent this critical brain drain?
The primary focus has to be on creating a fluid AI ecosystem, specifically one designed to facilitate cross-sector mobility.
Moving between industry and academia.
Right. Researchers often leave academia or government labs for high industry salaries, but many of them still retain a preference for fundamental scientific research. If there are no easy pathways like hybrid roles, joint appointments, or rapid sabbatical opportunities for moving seamlessly between industry and academia, the talent that leaves for the salary rarely returns, and that just cripples national research capabilities.
So it's about making sure the high salary doesn't necessitate abandoning fundamental science.
Precisely. Additionally, the sources recommend establishing a new central AI function within major research institutions like the UKRI, and encouraging all research funders to significantly increase investment in AI-enabled research, data, and infrastructure. This acknowledges that the state has to proactively subsidize the high-risk, non-scaling research that the commercial market is currently ignoring because of the commercialization trap.
Now, moving from national policy to real-world impact, the Transformers applications have moved so far beyond generating human language. The architecture proved to be a true general-purpose sequence modeler.
That generality is the most powerful takeaway. We discussed Inceptive using it to design complex RNA molecules for biotech. This application treats the sequence of 4 nucleic acids, A, U, C, G, as its own language, allowing the model to generate novel functional sequences just like it generates novel English sentences. It's accelerating scientific discovery in ways we previously thought were impossible.
And its impact is foundational in problem solving, like protein folding.
Yes, the AlphaFold project, for example, which uses deep learning to predict the 3D structure of proteins based on their amino acid sequence, it relies on architectural elements directly enabled by the transformer concept. It treats the protein sequence as data to be understood through attention mechanisms. It's completely transformed biology.
On the commercial side, the focus has shifted to compliance and security, as we saw with Cohere's strategy, which highlights a different kind of market constraint.
Cohere's success demonstrates that for many high-value enterprises, the most critical constraint isn't just performance. It's trust, security, and data control. They recognize that a model running on a competitor's public cloud simply won't suffice for banks or hospitals. Their focus on secure deployment, often involving running models on company premises, has unlocked markets that the consumer LLMs couldn't touch.
Let's circle back to the scaling issue for a moment. We noted that one of the architects, Ilya Polosukhin, points to a new constraint facing this massive scaling trajectory enabled by the transformer.
Right. He notes that the bottleneck in AI development is no longer just the immediate availability of powerful GPUs, which are now widely manufactured and distributed. The new constraint is electricity.
Electricity.
Yeah. Training and testing these truly large-scale models that might have 1 trillion parameters, requires thousands of GPUs running continuously for weeks or months. This places a massive, often destabilizing pressure on data center infrastructure and, subsequently, the electric grids worldwide.
So the next era of AI competition might not be a race for the smartest architecture, but a race for the most efficient, sustainable compute capacity.
Absolutely. The transformer model, by enabling scaling as the primary driver of performance, inadvertently turned AI development into one of the world's greatest energy demands. This shift mandates that future research must focus heavily on making these massive models significantly more energy efficient.
So, circling all the way back to the strategic blunder at Google, the core policy takeaway here isn't about protecting the written words of the intellectual property, is it?
No, not at all. The core policy failure was not in patenting the architecture. It was in managing the institutional environment that allowed the non-codified, critical implementation expertise, that complex, hard-won, tacit knowledge, to walk out the door. The control point shifts entirely away from the patent office and toward retaining the rare talent capable of exploiting the IP and driving the commercialization efforts themselves.
And finally, what does this environment, shaped by the diaspora and the transformers' dominance, mean for the next generation of builders? Ilya Pulasukian offered a powerful, optimistic piece of advice for students entering this world.
He emphasized the unprecedented opportunity. He said, "We're in a unique moment. 10 years from now, almost nothing will be built the way it is today." He frames it as a massive open field for innovation. And he offered this encouragement. If you understand computer science fundamentals and know how to work with AI, you can be 10 or even 100 times more productive than an engineer just a few years ago. The window to apply this new fundamental capability to build the infrastructure of tomorrow is wide open right now. Hashtag outro.
We've charted the rapid, dramatic history of modern AI, from a single transformative paper, Attention is All You Need, authored by 8 researchers at Google, to a multi-billion-dollar diaspora that fundamentally reshaped the entire competitive technology landscape.
It's an incredible story.
We saw how a seemingly abstract technical breakthrough became the engine of the most significant platform shift in technology since the internet itself.
And the story of the transformative diaspora is the ultimate corporate cautionary tale. Google's failure to recognize and capitalize on the full general purpose scope of its own invention and, retain its foundational architects, it gifted its competitors the key to massive scalable intelligence. The resulting loss of tacit knowledge forced them to compete directly against the very minds they trained.
The transformer architecture allowed us to build the biggest, most data-hungry models ever conceived.
It did. But if we accept that Lion Jones, the person who coined the name, is truly tired of the architecture, and we acknowledge that huge financial pressure is keeping researchers focused exclusively on scaling existing methods, this raises the ultimate question for you, the learner.
Will the next truly transformative breakthrough in AI, the successor to the Transformer, come from one of the well-funded startups founded by these original architects, using billions of dollars in capital to push the architecture to its absolute maximum limits?
Or will it require a completely new, irreverent, fundamental idea built in a quiet, overlooked corner, much like the original Transformer paper itself, far from the pressure of trillion-dollar market expectations?
Thank you for taking this deep dive with us.